In this video we will continue our investigation on electrodynamic balance. This time we will use electric current through metal as reference, which uses electrons as current carriers. Our previous experiment has demonstrated the effect of electrodynamic force induced by ionic currents, by comparing the voltage generated by different types of ions as current carriers. This time the left container doesn't contain liquid. The electric current will be caused by the flow of electrons through electrodes and an aluminum foil at the bottom of the container. Let's measure the resistance of the electrodes connected by the aluminum foil. We can get around 1 to 2 ohm, which is much smaller than the ionic solutions. Let's assemble the components, just like in previous experiment. These are the metal cans equipped with re-zeroing switch and terminals to measure the voltage. A corrugated plastic board is put on top of them to provide a stable base for the containers with electrodes in them. Let's start the zero calibration by measuring the voltage difference when there is no ionic solution in the containers, and no current is applied. After the re-zeroing switch is released, the voltage slowly drops to negative values. "10 minutes later, the voltage reaches negative 34 mV. A few minutes later, the voltage reaches negative 35 mV. Now let's prepare the salt solution for the right container. Here we have potassium chloride, magnesium chloride, and sodium chloride. Let's start with sodium chloride. Let's start the zero calibration for this sodium chloride solution. After the zeroing switch is released, the voltage slowly drops to negative values. A few minutes later, the voltage stabilizes at negative 22 mV. When the electric AC current is applied, the voltage slowly gets more negative value. It can reach negative 27 mV. The right container must be drained and flushed before its content is replaced with other types of salt solution. Now we will use potassium chloride solution. Just like before, we perform zeroing calibration first. When the current is still zero, the voltage reached -20 mV. When the electric current is applied around 1 ampere, the voltage goes to -38 mV. When the current is stopped, the voltage goes back to around -20 mV. After draining and flushing, the right container is filled with magnesium chloride solution. Just like before, we perform zeroing calibration first. When the current is still zero, the voltage is almost -23 mV. When the electric current is applied around 1 ampere, the voltage goes to -34 mV. When the current is stopped, the voltage goes back to around -20 mV. Here's the table showing the atomic weight of the ions involved in this experiment. We can see some correlation between atomic weight and the voltage generated in the hydrodynamic balance. But other factors must be involved, since the voltage is not simply linear to the atomic weight of the positive ion. Atomic weight of magnesium is closer to sodium, but the voltage is closer to potassium. Note that each ion of magnesium is related to 2 ions of chloride, while in the other salt solutions, the ratio is 1:1. But don't forget that we had already measured -35.2 mV even when the right container was empty. The table on the bottom right corner shows the voltage measurement relative to the empty calibration. But let's not forget that the alternating electric current applied to the electrodynamic balance were not exactly 1 ampere. Let's first calculate the change of voltage caused by the alternating electric current applied for each ionic solution. Divide those values with the corresponding ampere readings. Let's add the ampere-weighted millivolt to the initial voltage measurements. We can also observe that the final voltage readings are different from the corresponding initial values. Let's put these residual values in the table. Surely more research is needed to uncover the other factors influencing the results and their relationships in this kind of experiments. The other factors potentially affect the voltage measurements can be mentioned here. Temperature, air pressure and humidity of the ambient environment. Materials and dimensions of the containers, electrodes, and the base metals. Temperature of the solutions. Contaminations in the solutions. There might be other significant factors not mentioned here yet. Nevertheless, it's already obvious at this point that atomic mass of the current-carrying ions have significant effects to the electrodynamic force exerted to the electrons at the base metals, which were measured by the voltmeter. To get the mathematical model that completely captures all of those factors and their relationships, more data is needed. In my opinion, AI will be able to find the patterns and extract the mathematical equations which emulate these patterns.